start talking about the human vision system. I normally discuss the human vision system not in a lot of depth, but at least the basic understanding of visual processing in humans, just so that you get a feel for what are the capabilities, and in image processing, what we try to mimic, right? And there are a lot of things that we do when we look at digital images or digital visual content that we try to cater for human consumption, right? So as a result, basic understanding of what the good things are about the human vision system and what might be the limitations, right? Those are things to keep in mind. So we'll start off with a discussion on that, and then we'll talk a little bit more about the actual image formation process, right? So how do images get created, more specifically in the context of perspective projection, which is what typical sensors will use in order to capture a projection of the 3D space. And we'll also talk about the relationship between 3D to 2D and how we go use that in order to do quantitative measurements when you're actually working with images, digital images. Okay. All right, so human vision system in general, we want to try to understand, because like I mentioned, I think about a week ago, a lot of your brain is dedicated to just processing information that is coming through from the two eyes. Right? So 2/3 of your cerebral cortex and your sensory neurons are overwhelmed with just trying to process visual input. Okay? And as a result, there's a lot that goes on that is driven by visual processing in the brain. In fact, if you think of the different stages in which vision plays a role on how you actually perceive the world, you can think of it in terms of just the image formation process, right? How do you form an image from a 3D world onto a projection, if you will, in the brain, right? And of course, the sensor in that case would be your eye. And so if you want to understand what is the formation process, how do we actually get stimulated by light, if you will? And then there is the imaging process. So what is the optics involved, and how do things project onto the retina, right? Retina being our visual sensor in the human system. And what is that sensor comprised of, right? So it's a bunch of photoreceptors, and that is somehow forming if you will, a contiguous representation of the 3D space, right? So obviously when we look at the world, it appears continuous to us. Right? And how is this continuous world represented in the brain? So if you think of it, you look at the room, you see the 3D space, and everything is contiguous. Do you really think that that's how the projection is? Is that what your brain is sensing? I mean, this is something that we don't fully appreciate. Neither do we understand the complex biology that is involved, right? I mean, you can think of light sort of, reflecting off of all the surfaces in this room. Portion of the light is actually getting absorbed through your optics. It's projecting onto the retina, right? The retina is supposed to form an image. But do you think that it actually forms an image just like we think of using a camera? You take a picture using a camera and you get an image, right? Do you think it's the exact same process that's going on in your human eye? Is the eye equivalent to a camera, and you think we get this nice contiguous representation? And the answer is no, right? We don't. So there's a lot of processing going on beyond just the projection process that your brain is involved in order to recreate what we think is this 3D space. Obviously, our eyes don't have infinite resolution, right? So there might be other things in this room that are actually present, but we are just unable to perceive it. Right now, simple things, right? We have a projector going on in the room, right? There's light coming off of it, and we see this as, please come in. We see this as a nice projection on the screen, Right? There are tube lights, right, that are on in the room. They seem just, providing a constant source of illumination in the room. Do we think that is all true? Absolutely, it's what we see, but do you think that's true? Is that reality? Right? If I tell you that this tube light actually is flickering, would you believe me? It's continuously flickering. It's not constant at all. Right? It's flickering non-stop. Right? But that we don't understand, we can't perceive. That's right. Absolutely true. Right? So the projector is flickering as well. The light sources are flickering. It's just that we are unable to perceive it. It's just our vision system is not capable of picking up that reality. But it is reality. It's just that we cannot see it, and as a result, for us, this is reality, the fact that it's continuous, right? It's not flickering. So there are limitations in terms of what our optics are capable of perceiving, what our brain is capable of processing. But there are other things that we actually are filling in, right? There's information that your brain is actually filling in for you, which we don't even realize. Now, in most cases, that turns out to be great, right? Works for us because we live in a world where, it's filling in the information appropriate to our needs for processing and doing certain tasks. Other cases, those limitations actually fail us. Right? Well, hopefully not in a bad way. Right? So can you give me an example where, in real circumstances, outside of these examples of flickering lights, where your visual system might actually fail you? Right. I'm sorry? Sure, of optical illusions, absolutely. Right. But give me a good example of what, you observe in almost day-to-day life. Blind spots. Well, okay, blind spots, well, unfortunately, they're not optical illusions, right? That's a reality of the optics of the eye. So that's part of the mechanics, if you will, that results in a blind spot. Now, of course, as we walk around, yes, okay, well, that's true. But at the same time, right, if you think of it, we know physically your eye actually has what we call a blind spot, and we'll look at the actual mechanics of it. But when you walk around, it's not like, there's a patch of darkness around you, right? It's not there. Even though your eye actually is unable to perceive a certain portion of the space, it doesn't feel that you actually see that all the time, do you? So the brain is filling it in for you. What else might be a good example? Yeah. The road? Right. Well, okay. Mirage. Mirage is again, it's a physical phenomena. It's not an illusion, if you will. So it is a physical phenomena, and you interpret it in an appropriate way when we see certain variations in pressure, right? But it's not specifically an illusion created by the limitation of the eye. Now, perspective projection, right? When you have a pair of lines going in front of you and you think that they're converging at some point, again, that is not necessarily an illusion. Right? It's not a limitation of the eye. That's just the reality. That's just physics. Okay. Yeah. Well, we don't necessarily tend to ignore them. In fact, we tend to, expect that if you have smooth patterns, right, something that's continuous, that doesn't represent information that is absolutely vital. Right? So when you look at the wall, if you will, right? In the back, it's pretty much all a constant shade of color, right? In general, you're not going to see subtle variations if they exist on the wall. Okay? It's not that they don't exist. If you go really up close and try to find them, you'll probably find them because you're looking for them, right? But by definition, it's not going to stand out as something that's vital for completing a specific task, right? There are other things in the room that will stand out much more than probably some variation in the shading on the constant wall. But in terms of simple examples, right? I mean, you guys see cars drive by all the time, right? Have you ever sort of seen, one of these hubcaps that have a lot of spokes? And it feels as if, the wheel and the motion of the spokes, they don't sort of match very well. I mean, they're not moving in the right direction, right? Now that, well, I mean, it's not possible, right? Yeah, I've seen cars where they have these things on some kind of a rotor, right? So it's mechanical, but that's not what I'm talking about. I'm talking about things that are not motorized and they're just moving in a normal direction. Now that is an illusion, right? So why do you think that illusion happens? Very good. So the same reason why we cannot see this light flickering is the exact same reason why we see that moving in the wrong direction, right? So the concept for basic perception is something we call aliasing, right? It's a matter of how quickly we are able to sample something that is changing in time. Right? Now the vision for us, and in general for any artificial sensor that we think about, that phenomena holds true both in space and time. Okay? So our ability to perceive things that exist either in space or in time is entirely dependent on how often we are able to sample a particular event of change. Okay? So if that wall is textured, I cannot see it from out here. Right? I really can't see if that wall is textured. I don't even know if it's textured. You guys at the back might know better. Right? But the reality is that it's not that I am unable to see it if I come close enough to it, right? If it's textured, if I'm very close to it, I'm able to sample it, right, at a high enough resolution where I should be able to see the texture. Standing so far off, I can't see it, okay? Just because I can sample it. So the same things happen in time as well in space. Okay? The example of the spoke moving, that's a time sampling example. You cannot see something in space, that's a space sampling problem, right? If you cannot see a certain texture. All right. Now, of course, all of that happens at the sensing process, right? Once we sense something, then there are two levels of processing that we typically distinguish vision processing in. Something that we call low level and something that we call high level, right? Low level processing is predominantly involved in looking at primitives in terms of observations or in terms of useful information that's present in the sampled signal. Okay? And when I talk about primitives, we're talking about things that are defined at a very, very low level, things like, sharp transitions, contrast changes. You have an edge somewhere, right? So a particular color stops and a new color starts. Those kind of changes is what we're talking about in terms of low-level processing. Now, how do you take those small observations and put them into higher abstract concepts, right? How do you say, I look at this chair, right, and I see, well, there are many places where contrast changes happen, right? I see a flat surface here, pretty much, having, let's say for now, some constant illumination. At the edge of it, there's a change, right? This side there's a change, this side there's a change. How do you take all these changes, put them together, and construct a shape? Right? Now that is really what I'm talking about in terms of higher level processing. Right? So you take small primitives, put them together in order to define higher level abstractions, what we call shapes. Right? Shapes are something that we define as a particular kind of geometry. Right? Now if you think of it and think about broader abstractions, we call this a chair. Yes? Think of why do we call it a chair? We call a lot of things a chair. Not all of them have the same geometry, right? Not the same shape. These days chairs come in all kinds of forms. Very interesting artistic creations, come across as chairs. Why do we call them chairs? Function. Very good, right? So there's a specific function involved. Right? The function is, you sit on it. Right? Now, think of how do you take low-level processing to the level of abstraction where you can generalize something to say, this is what I sit on, and as a result, I will call this object a chair. That's a very difficult abstraction, right? If you try to generalize it, that's very, very difficult to do. Now, it turns out, the human brain, in terms of higher level abstractions, tends to build representations from low-level primitives. We don't know exactly how they build it. And at the same time, it feeds off of an internal memory, if you will, right? So, back in the 60s and early 70s, there were studies done on the human vision system in terms of how many distinct objects do humans recognize, right? It turns out, well, at that time at least, the number was roughly in the order of 10,000. Yeah, well, not at the same time, but we recognize up to 10,000 distinct objects. Right? Now, you sit there and say, well, 10,000 doesn't seem like a whole lot. Right? But think of 50 years of image analysis research. What's your best guess as how many objects do you think an artificial vision system is capable of recognizing? 500? Any other guesses? It's actually not even 500. Right? You're talking about a handful of objects. Really. Below 100 objects is what an artificial vision system is capable of recognizing. We still haven't figured out how to take primitives and come up with generalized abstractions. So, in terms of human processing, we have a reasonable idea of what's going on at the low level, right? So, in the low level is primarily dedicated to your visual cortex, okay? So, your visual cortex, your eye sees something, gets sensing, and it sends it back all the way to the back of your brain. That's where your visual cortex is, and that's where low level processing happens. That's where primitives are abstracted. After that, the signal is sent for higher level cognitive processing, and we don't have a very good understanding what happens there. Okay? So as a result, a lot of artificial heuristics as well as algorithms, mathematical models have been proposed of what happens in higher level understanding of images. But those are algorithms and mathematical models. We haven't quite bridged it to the human vision system. Okay? All right, now obviously we do certain things very well, and we do a lot of things without really thinking much about it. Right? If I just throw something at you, right, I mean, most of you here are going to see it, you're going to probably catch it. Okay? That's something that you do as a reflex more often than not. But think of what is involved in actually doing that. It's fairly complex, right? You have to first identify an object that is coming towards you, right? And you're going to identify that object among all the other objects that are present in the room, right? So obviously you're seeing a lot of things, right? But you're going to somehow identify and focus onto that object. You're going to lock onto it. At that point, you're going to actually try to figure out its trajectory. Right? You're going to guesstimate its velocity. Right? You're going to say, okay, the object's coming toward you. You're going to figure out and estimate its size. In fact, by looking at it, you're going to estimate its size and weight. Right? Once you do that, that's when you actually get to trajectory. You're going to figure out when it's going to sort of start coming towards the ground, coming towards you. You're going to position yourself, move yourself. You're going to articulate, whatever you need to articulate, both limbs. In order to position yourself, open up your hand and actually grasp it. Right? And grasp it so that it actually doesn't fall off. That's a lot of processing that we're talking about. Right? And all of that happens in an instance. You don't really think about it. It's just happening. Now, if you have to actually recreate this, right, for an artificial system, think of all the calculations that one would have to do. What would be your actual algorithm that you would have to write? How many lines of code do you think that will amount to? A fair amount, right? A fair amount. To the extent that, think of it, 15 years ago, we couldn't even do this on a computer, on a desktop computer. Yeah, nowadays, you can calculate all of these things. But 15 years ago, no. You could not. So a lot of processing is going on, and it's our job to come up with an understanding of what is involved in each of these things, break it down into small problems, small things that we can actually compute and write algorithms about, piece them together in order to recreate what we do without even thinking about it. You don't even consciously realize it. I ask you to walk out this door. How many of you think would actually bang, on the sides of the door? Anyone? No. Right? Think of what it takes to do that. That's not easy, actually, for a robot to do. Right? Back in the early 90s, right, I spent 3 years working on a vision system just to get a robot to walk through the door without hitting the sides. It took me 3 years of work just to make that happen. Trust me, it took a long time, and there are so many things that you do not realize. Right? So, all of these things, is what we have to think about. You have to think of things that you normally do not think about. Right? Those are subconscious actions, processing tasks for you. You have to start thinking of them. That's really what image processing is about. Right? Image processing, and that's, again, I sort of say the same thing again that I said last week, which is there's a certain amount of creativity that is required in image processing. Because it requires us to think of what your brain is doing, right? Now, there is no answer, or at least there is no known correct answer, right? It's your interpretation of what you think is happening, right? And you're going to try to recreate that. And as a result, you're going to come up with your version of what's happening, and that's going to be your algorithm. It's going to give you a certain kind of results for images that you process. Right? And that's what makes image processing fun and interesting, because every time someone thinks of it, it's their interpretation, their creativity into it, gives you interesting results sometimes, sometimes not. Right? But that's what we are here to find out, and that's what makes it fun. Okay? All right, now, things that we are not very good at. Okay? Visual sensing for us is relative. Our visual sensing system is not absolute. Okay? Can I tell you, how far am I sitting from him? Yeah, maybe I can guesstimate. Right? Maybe 10, 11 feet. Maybe I'm wrong, I don't know. Right? I can't really tell you exact measurements. What I can tell you is he is closer to me than the person behind him. So I know relative things. Now, of course, relative things also can be misleading for us. Okay? So here's a very simple example of an optical illusion. This is something called the Mueller-Lyer illusion. Okay? You have two lines, right? Which one do you think is longer? Right. What is it? The illusion is the giveaway, I guess? So obviously they are both the same length. Right? So is that your vision talking or is that your brain talking? Does anyone's eyesight tell them that they are the same? No. Right? The blue should be longer, I hope, than the red. Why do you think that is? That's right. So if I take away the ends of the lines, all of a sudden they'll look the same. The reason one looks longer than the other is because of the fact that when you put these corners, the bindings around the line that are at an acute angle to the line, it makes it appear compact. And the compactness makes you think that this must be smaller than the other one, shorter than the other one. So your vision system is actually seeing it, but your brain is providing it feedback saying that, well, you know, because of the contrast around it, the way it appears, it has to be shorter. Right? And as a result, that's what we believe. Obviously, the raw signal being projected is not so. It's a feedback from the brain that makes it happen so. Okay? Here's another example. You find a black dot in there. Right? So there is no black dot in there, right? But obviously you see it moving around everywhere, right? You cannot quite focus onto it. So the vision system is actually dynamic, right? It looks at contrast changes and is expecting certain contrast changes to continue in space. Okay? Now, you have essentially a shading, right? You have black and then gray stripes, and you have a white dot in the center. Right? Now, it cannot quite make out whether the transition is exactly always that. All it is looking for is the repetition to happen. Right? And every time you try to focus in to something, it's expecting that repetition to keep changing, and your eye is in a constant mode of saccade. Right? Our eyes are never fixated. Right? Our eyes are constantly moving around. It's continuously sampling in different spaces all the time. And as a result, it can never fixate on a single dot. It just expects to see this contrast. It'll always keep moving. Again, your brain also provides a lot of feedback in terms of what it sees. Okay? And again, this is an example of the dynamic nature of the eye. If I ask you what this is, right, depending on where you focus, either you should see a goblet or you should see two faces. Once you realize that, intermittently you'll keep shifting between the two. That's again dependent on where your eye actually saccades at any given time. Right? Now in this particular case, you know, the dynamic content in this particular image is not as great as the one that we had before. Right? The variations are not as large. And as a result, the transition should be much slower. Right? You should be able to actually see the object for a little while before it might switch. Here's another example. You see a lot of lines in between the checkered patterns. Right? And each of the line might be bending in a different way. Of course, the reality is that they're all parallel lines. None of them are bending. Okay? The only reason you see them bending is based on how much of an offset there is between the blocks, between any two rows. Okay? If I change the offset in a specific order, right, make it shorter or longer, the line will bend in a particular direction. Again, this is part of illusion. It's not reality. Again, it's a matter of seeing specific contrast variations occur in the scene. So the human vision system is very, very sensitive to contrast changes. We are not very sensitive to constants. We are sensitive to changes. In fact, would it surprise you if I told you that if you had the ability to put actually a probe into your visual cortex and recreate this scene, that the only thing I would actually see is places where there are contrast changes. I would not see anything constant in that recreation. So the first level of processing that happens in your visual cortex is to identify contrast changes in space. All the constants, just ignore it. The vision system is also very good at filling in things. Okay? If you see, for example, the picture on the upper left, do you see a faint red circle over there? Do you see a faint red circle? Yes? Kind of. On the upper right, you see a blue square in between all the circles. Yes? Do you think it's there? It is not there. It is not there. It's what your brain is filling in. Your brain doesn't like discontinuities. Okay? In general, it doesn't like discontinuities. It likes to see complete structures. Okay? So whenever it gets a chance, if it collects enough evidence that there might be a complete structure somewhere, it's what it will provide as feedback to the vision system and say, no, that has to be a complete structure in there. Right? An incomplete structure would violate what we see or more commonly observe in a continuous world. And as a result, it will try to fill it in. Now, of course, if I, move the red spokes around just a little bit, all of a sudden you won't see the red circle anymore. Right? Because now there are discontinuities in those edges. Right? They're not aligned anymore. And as a result, the brain actually sees them as two separate objects now. Right? Doesn't need to provide a continuum to understand it. Okay? Same thing. Right? If I sort of define exactly where the contrast changes are, it will start breaking up. Doesn't need to create a full square within that anymore. Right? Now, again, if I actually keep the thing straight, but create breaks, create gaps between the red lines and the black lines, again I get a sense of two separate objects. Right? And I'm able to perceive it accordingly. So these are things that your brain actually does in order to alter what we think we perceive. Now, of course, these are what you may call illusions, or this is a way to understand what might be the limitations of just the vision system, right? And the limitations come primarily because of the fact that your brain is trying to fill in information that may or may not be there. Most of the times, it actually does a good job and fills in the right stuff, right? Only there are certain cases where it might falter in trying to provide a sense of generalized reality. Okay. Now let's come back to the optics of the eye, right? In general, when we look at the optics of the eye, and you know, people have studied the optics of the human eye for a long time in order to model artificial vision systems, right? And the optics is fairly simple. The important optical structures that we have are fairly limited. You have the cornea, right, which is the outer covering of the eye. Right behind the cornea, you have the iris, which is actually a muscle structure that controls the pupil, right? Think of it as an aperture of how much light actually gets through to the sensors, the retina. Okay? And behind that is your lens. Okay? The cornea is fixed structure. Okay? The lens itself is quite flexible, right? Till we age, right? As we age, that structure becomes more and more rigid. But otherwise, for young eyes, the structure is very, very flexible and is able to bend itself in order to generate very, very high curvature, as well as stretch itself in order to make it as flat as possible. Okay? And that's what allows us to focus objects that might be at varying distances. Okay? So the basic optics is relatively simple. Now, of course, there is, if you will, a point of central fixation, which means that there is a line that joins the cornea, passes through the center of the iris, and connects back into your lens, which forms a straight line going back to the retina, which we call the optical axis, the optic axis. And in general, our eye, or the sensors behind on the retina, are fairly symmetric around that optic axis, except for the blind spot. Okay? So this is what the structure looks like. Now keep in mind, we have liquid both right behind the cornea and of course behind the lens. Okay? The purpose of this liquid is primarily to keep the shape. Okay? If there was no liquid, everything would just collapse onto itself. So the first purpose is to keep the shape, and the second purpose is to continuously provide nutrients to the sensors and the cells that are present. Okay? Now, the optic nerve is where all your sensors come together as a bundle. So the back portion here is the retina. Okay? Retina has photoreceptors, among other cells. All of them send out signal. They come together as a bundle at the optic nerve and transfer that nerve back to your visual cortex. Okay? Now, of course, where all the sensors come together and forms the optic nerve, we have no ability to see because there are no sensors there. Okay? So that's what we typically call the blind spot. Now, your eyes, the optic axes are such that they are actually not, parallel to each other. They actually converge at a point in front of us, and the optic axis is offset towards the temple. Okay, so it's 5-degree offset towards the temple. The cornea itself forms the main refractive structure for us, okay, and has a very, very high index of refraction. It's in fact almost equal to water. The reason for that is because the eye essentially wants to collect as much light as it can. Right? So having a high refractive index means we are able to bend rays of light more, right? The higher the refractive index, the higher the bending power. You can think of it that way. So having a high refractive index for the cornea allows us to actually sample light from directions that are not just entirely straight, but peripheral to us. Okay? So it allows us to collect as much light as possible. The iris, of course, is there so that if there is too much light, it will contract and minimize how much of it is sent through the lens. Okay? Of course, if there's very little light, it will open up wide, it will dilate. Okay? So it serves as an aperture for your optic system. The lens itself will bend depending on what you're focusing on. Right? So if you're looking at something very close, it will bend itself a lot, right? Because you need to project a fairly decent sized object very close to you so that it can fall and project itself onto the retina, right? so the sensors can sense it. If you're looking at an object that is very far, obviously it's not going to appear very large in size, so the lens doesn't have to curve itself all that much in order to project it back up to the retina, so it stays flatter. Okay? The transmittance of light is also important. So, our vision system, we typically see things in the visual spectrum, right? Remember we talked about the EM range, the EM spectrum, that's very wide, right? And we sense a very, very narrow range of wavelengths within that. Your eye can only see a certain narrow range of wavelengths. So the amount of wavelength that gets transmitted through the cornea is generally going to be above 320 or so nanometers. Everything under that, it doesn't send through. So the transmittance curve of the cornea itself is such that everything under that wavelength, it will cut off. Everything that is under 380 nanometers will be cut off by the lens. Now in general, when you think of wavelength under 380 or 300 nanometers, what kind of light do you think of that as? Infrared on the other end. Sorry? Very good. This is ultraviolet light, right? So blue light. Blue light in general, not good for living systems. Right? I mean, you hear this all the time, right? You go out in the sun, you want to put some protective cream and so on and so forth, which will try to reflect UV light away. So UV light in general is damaging. In fact, it kills cells. Right? You don't want that going through directly onto your photoreceptors because it will kill the retina. Right? So you have built-in mechanisms in order to actually reject all the UV light going through. So the first layer is the cornea. The second protection layer is the lens itself. Okay? Now, the retina in general will receive light within the range of 380 to 950 nanometers, right? So this is the visual range we sense in, 380 being blue, 950 being infrared light, right? So IR. Now, of course, as the lens ages, it's going to change its transmittance, okay? So it becomes yellowish in color, right? As we get very old, you have heard the term cataracts, right? Cataract is nothing but the complete yellowing of the lens where the transmittance power drops so low that there is very little light going through. Right? So that's when one may talk about lens replacements and things like that. Anyway, but the visible range that we typically care for is within the range of 380 to 770 nanometers. That's our typical transmittance range where we have pretty high transmittance. Your transmittance curve, by the way, is not flat. Right? You don't send every wavelength of light equally through. Okay? So the transmittance curves of the lens and the cornea vary according to wavelengths. Okay? If we talk about white light, about 70 to 85% of white light normally is transmitted through to the retina. Okay? So what is white light? Sorry? All the colors, very good. So for us, normally when we think of white light, when we talk about lens systems and we talk about white light, it's essentially the integral over the sensing wavelength range that we are talking about, right? So if we talk about visible 380 to 770 nanometers, it has all the three colors. You integrate over all the transmittance of those wavelengths, you get an integral of what light goes through and what we call white light. Right? So equal proportions of all integrated over through the transmittance curve. Okay? Now the photoreceptors will all sense the wavelengths coming through. Now photoreceptors in fact are fairly protected. Okay? So it turns out that if you think of a camera, right, you have photoreceptors right on the chip. Right? So you have a lens system in front. You have light coming through and it falls on the chip. It gets charged, and the charges transmit, they're digitized, and you get an image. Right? Well, the human vision system is not quite the same. The photoreceptors are not there front-facing to actually see the light coming through. In fact, it turns out that they are buried several layers behind on the retina, and they're actually backward facing. So the light has to traverse through several neurons in order to get back to the photoreceptors, turn around, and get sensed by the photoreceptors. This is the way the retinal layers are constructed. And it's a way for the vision system to protect the photoreceptors from failing, okay, for all kinds of reasons. Now the receptors actually come in two shapes. Okay? They're literally different shapes. One of them is more conical in shape and we call them cones. The other is more cylindrical. We call them rods. Okay? So they each have different functions to play as well. Rods are basically used for low light sensing. And rods are unable to differentiate between any color. Okay? All it can sense is raw power, right? Raw integral of energy coming through across any wavelength of light. It cannot differentiate between wavelengths. Cones, on the other hand, are what we call our color photoreceptors. Okay? They come in three flavors: red, green, and blue. That's what we call them because that's how we think of, separation of colors in a continuous spectrum of light. Okay? So the cones are generally the ones that are active or predominantly used for color sensing or daylight sensing. Okay? Our color sensing capability at night is very poor. You don't see colors very well in low light situations. And that's because the cones are not the primary photoreceptors in low light environments. It's the rods they are. And the rods don't see color very well. Okay? They don't differentiate at all, in fact. Okay. The rods themselves tend to be very small. They're 1 to 2 microns in diameter. Cones are slightly bigger. They're 2 to 3 microns in diameter. Okay. Now, cones are extremely concentrated and densely packed at the fovea. Okay. Fovea is the region around your optic axis. Okay. The point where the optic axis intersects the retina is your fovea. And a narrow region around the fovea is where all the cones are densely packed. Okay. As you go away from that, the packing density drops dramatically for cones. Beyond about 20 degrees, it kind of stops. You have rods all over. Okay. There are no rods in the fovea at all. Okay. Their density increases away from the fovea and then it becomes fairly sparse as you go towards the periphery of the retina. Okay. So as a result, if you think of it, the density is representative of what? Ability to perceive color, yes, but what else?
I think it sort of defines focus.
Very good.
Around it you'll perceive more contrast and silhouette.
Yes.
Where in the center you'll perceive more detail because it's more color.
Very good. So detail. What does detail translate to? Not just amount of light, but remember that the packing density of cones, right? Having a lot of cones, what does that amount to? Resolution. Very good, right? Detail, resolution. So it amounts to very high resolution. So if you look at the retinal structure, it turns out that we don't actually have a constant resolution when we see things. It doesn't seem like it, right, when you look around. But that's what it is. We do not see everything around us at the same resolution. We only see details or the highest resolution when we are looking straight at an object. You can try this, right? I mean, you can look at, at least for you guys who are sitting closer up front, I don't know how well it will work for you further back, but if you look at the screen here and try to read the text, as you read the text, shift your eyes away from it and see if you can still keep reading it. Right? You will see the shades on the periphery. You can see the contrast changes. You can see the blacks, the whites, but you can't read it. You lose the ability to see that detail. Right? That's because we do not have the same resolution away from the fovea, the central point of fixation. That's also the reason why anytime you want to look at something small, what do? You bring it right in front of you as close as possible, because that's when you will see the detail. That's where you get the best sampling. Now, on the other hand, how many of you have ever looked at stars? Use telescopes to look out into space. All right. What do they teach you when you start learning about telescopes and looking out at stars? The first thing they teach you is don't point your telescope directly at the stars that you want to see. Do they teach you that? That's true. You know why? When you're trying to see distant stars, there's not a lot of light coming through, right? Very little light coming through. You're going to see faint objects. If I look directly at faint objects, what will happen? Where's the light going to focus? Sorry? On the cones. Very good. Are the cones any good in low light? Cones are useless. Can't sense any damn thing in low light. Right? It's the rods that would be required to actually see in very, very low light conditions. So if I want to see something that is extremely low lit, I want to not focus directly at it. I want to focus slightly away from it so the lens or the light actually falls on my rods, away from your fovea. And the minute it falls on the rods, then I should be able to perceive it and see it. Okay? Now the color vision, of course, we don't, even though we say that we have these three distinct kinds of cones, we don't actually see, red in certain areas of the image, green in certain other regions, and so on and so forth. We don't actually see separate colors, right? We still see a continuous range of colors, right? So we sense across this broad spectrum, okay? And the color we perceive is simply an integral of each type of cone that actually got activated by a specific wavelength of light falling on it. Okay? So if I look at actually the sensitivity, I'll come back to this in a second. If I look at the sensitivity of my cones, you would expect to see sensitivity curves that look like this. Okay? So the blue for blue receptors, green for green, and red for red, of course. If you see, they tend to overlap quite a bit. Right? So every photoreceptor is capable to a certain extent of sensing across the full spectrum of wavelengths. It's just that the amount of energy that they would actually collect is not the same. It varies. Okay? So whenever we see color, it's truly an integral across all these wavelengths, and that's the color that emerges. Right? And we would see it as a part of the continuous spectrum. Okay? Now, in general, each of the cones that we have, they do have a peak sensitivity at a particular wavelength. Right? It turns out for the red, it's 580 nanometers, for green, it's 540, and for blue, it's 450 nanometers. Okay? That's when we have the highest sensitivity. Everything outside of that, it decreases. Now, on the other hand, for the rods, you're not, there's a sensitivity curve across the entire spectrum. And it turns out that, they typically tend to have the highest sensitivity around 550 nanometers. Okay? But they still have a full range across 380 to 770. Now, for the perception process, there are several factors that play a role in how well we are able to see things. Okay? Contrast being the first one. Okay? Now, contrast is simply a relationship between the luminance of an object and the luminance of the background. Right? So, how much variation there is in the basic luminance of things in your visual sight. Okay? So, things that are obviously very dark and very bright will have the highest contrast, and we'll see them most clearly. Things that have very, very small variations in shades of color, we don't see them very well. Okay? So the contrast is an important factor in our ability to sense things. Size is another one. Right? Not the actual size of the object per se, but the size of the projection of an object onto the retina is what matters. So for example, if you're trying to look at a very, very small object, you put it through a bunch of lens systems and magnify it. As long as the projection is large enough on the retina, you'll see just fine. You'll see all the details. Right? So it's the projection of the object on the retina that matters, on how well we are able to see the details of that object. Okay? And the other factor is time. The visual system is purely photochemical. So things that are moving very fast in time, events that are changing in time very fast, that do not allow sufficient interval between photochemical processes, we simply cannot sense them. Okay? So time is another factor. If you have a very bright object, it's going to provide a lot of light, it's going to flash very fast, yeah, we may be able to see it. A very dim object flashing at the same speed, just not enough time for us to collect all the energy and process it. Okay? So time is important for the visibility to work. Now, the basic facts about how the eyes are situated. The distance between the eyes is 6 centimeters. Now, when we study, so the question is, when you separate the eyes, what does that facilitate? The separation of 6 centimeters, what does it do? Depth perception, very good. How? Right. Very good. So, but what does that do? What does that do in order to help us do depth perception? I see two pictures, right? They're separated from each other by a certain distance, right? But what does that separation amount to? How does that help me get to depth? Very good, very good. So we are going to do triangulation in order to get back to depth information. But in raw terms, things that are close to you will separate out more than things that are further away from you. Right? So just by knowing that a particular point in space is projecting on both the eyes, right, on the retina, if I were to figure out how much they are separated by from an absolute point, let's say the optic axis, it can tell me if that object is closer or further than some other object that projects onto the retina. Okay? So again, it's giving us relative information. It gives us depth information from that standpoint. This separation is what we typically call or refer to as disparity. Right? And we'll come back and study this, how we actually use it for triangulation purposes as we talk further about stereo vision. But that's one of the reasons why we have eyes that are separated by a certain distance. Okay? The eyes are, of course, roughly about halfway down your head. The visual field that you actually see for each eye is quite interesting. For a monocular vision, you get about 160 degrees width, 175 degrees in height. Okay? That's a fairly large visual field that we have. When you go out and buy a wide field lens, what's your visual field? How many of you are photographers here? Like to take pictures, cameras? What do you think is the visual field for a wide field lens? Oh, yes, well, fisheye, yeah. Now, fisheye is huge, right? Fisheye is almost 180 degrees. But for a wide field lens, no. Sorry? It's about 60 to 80 degrees. That's what we get with a wide field lens. So just your monocular vision is quite thorough. Right? Now, of course, you combine it with binocular vision, you get 200 degrees field of view, right, in width, about 135 in height. Okay? Now, remember, this is just field of view. This is not this full space where you perceive depth. Okay? Where you actually see stereo vision is going to be about 120 degrees by 135 degrees. That's the range where images will overlap for the two eyes. Okay? So our depth perception ability is limited to about 120 degrees, 135 degrees in height. Okay? All right, what else? Some basic things. Your retinal area generally is about 5 centimeter by 5 centimeter. The thickness of your retina is about 0.4 millimeters, fairly thin. 1 degree of visual field on your retina is going to be about 0.3 millimeters. You normally stretch your hand out and put your finger up. That's generally about 1 degree visual field. The finger is going to project onto about 0.3 millimeters of your retina. You have about 5 million cones in each of your retina, 100 million rods in each retina. Okay. Peripheral vision is very, very important for us. Okay. We may not see details around the periphery, but it's very important because obviously it's a defense mechanism. Things that you cannot see in detail, you want the smallest change in contrast to be picked up. Low light changes. Right? That's what rods are great at. So you have lots and lots of rods all over the retina except for the fovea. Right? So you have 100 million rods. The diameter of the fovea is about 5.2 degrees, 1.5 millimeter. Right? So this is where you see your best. About 5.2 degrees, that's it. Okay. Now the minimum number of absorptions for any kind of detection, for any photoreceptor to actually sense something, for rods it's just 1. Right? Low light detection, scotopic detection is 1. Okay. Sorry, for rods normally it's just 1. A single photon of light coming through will fire it off. For scotopic detection, in order to actually differentiate something, it needs about 1 to 5 photons coming through at night time. And of course, for photopic detection, you need 10 to 15. Right? Much higher number of photons need to come through during daytime. Okay, so any questions on the human vision system? Everything good? Okay. All right, so let's translate the basic optics that we looked at into a very simple projection model so we can start creating relationships between what we see in 3D space to what gets projected onto our retina or, for that matter, any other sensor that we can talk about, right? So the process of projection is relatively simple. What you have is an object that exists in 3D space, right? It's going to get illuminated by some kind of a light source, and it's going to reflect a portion of that light. The reflected light is going to pass through some kind of a lens system, and it's going to project back onto a sensing surface, right? Whether this be a retina or any other kind of sensing surface. Now, of course, if you look at the basic geometry of rays, it turns out that a projection system like this will always generate an inverted image. Right? So by the way, does this hold true for the retina? You think the projection is inverted for the retina or not? Yes? Right? Yes, it is. It is. So the same ray system works for the human vision system as well. Now, of course, the distance between the sensing surface and the lens is typically referred to as the focal length. Right? This distance is usually fixed. Okay? Now, the simple projection geometry results in what we call perspective projection. Okay? Perspective projection is nothing but a reduction in dimensionality. Okay? When you're working in 3D space, we have 3 dimensions, x, y, and z. The projection of the 3D object is going to get projected onto a 2D surface, resulting in a loss of a dimension. And the loss of the dimension being depth. Right? All we know is that the projection is going to be a certain distance behind the lens. We do not know how far the object is in front of the lens. The loss of dimensionality is what we call perspective projection. Okay? Now, of course, there is a relationship between the 3D object, its size, geometry, to the 2D projection. Right? And we'll try to understand what this relationship is, but we'll define for that first a coordinate system. Okay? So for the real world coordinate systems, the 3D space, we'll refer to everything in that space with capital X, Y, and Z for the 3 dimensions. The origin of that space will be at some arbitrary 0, origin, okay, 0, 0, 0. And in terms of defining our optical geometry, we'll define that origin to be at the center of the lens. Okay? Now, for the image that gets projected from that object, we'll define an image coordinate system, and we'll refer to that with smaller letters, small x and y denoting the 2-dimensional coordinate system or the projection. Okay? And we'll assume that the plane on which the image is projected is parallel to the 3D plane. Right? So in general, that plane would be perpendicular to the z-axis. Okay? We'll also say that the optic axis of both the coordinate system pass through the lens center. Okay? So the origins are all in line. All right, very good. So if I convert that simple drawing into our planar projection system, what we have is some plane in the 3D space, right? The plane on which there is an object, and the plane is parallel to the xy coordinate system. It's going to project back onto our image plane, the plane being parallel to the world xy coordinate system. And, of course, the origin of the 3D coordinate system being the center of the lens. Okay? Now, if we assume that the center of the lens is just a small hole, right, we can think of this as what we call a pinhole projection system. Okay? Now, there are subtle differences between pinhole projection systems and lens projection systems. A lens projection system, by definition, allows for a lot more rays of light to pass through it than just the one in the center. Okay? A pinhole system is the one that will reject every ray of light except for the one that passes through its center. Okay? So we'll make that assumption for now. So that's the easiest way of defining how these geometries relate. Okay? Now, of course, rather than actually having a focal length that's behind my lens, if I simply take it in front of the lens by the same distance f, I would end up with what is called an upright projection system. Right? The geometries don't change. All I now have is a projection plane that is the same distance in front of the lens. Okay? This assumes that you have a lens which is perfectly symmetric. Okay? So we can look at this geometry, it's much easier to relate to because now you have projections that are upright. Right? Things are not inverted. First, that, and second, I don't want to work in negative coordinate spaces. Right? All right, so let's look at a single point in the 3D space. Right? We'll call that at some point A, comma B, comma C. Okay? That point is going to project onto our imaging plane at a point small a comma b. Okay? Of course, this plane, remember, is a certain distance f in front of the lens. Okay? Now, this diagram should show all the coordinates that we have for the simple projection model. Okay? Now, how do we relate? What is the relationship between this a comma b and the point that exists in the 3D space, A, B, and C? Okay? So to do that, one way to define that is simply by looking at simple trigonometry, or in this case, we'll look at equal triangles, right? The laws of similar triangles. So the laws of similar triangles tell us what? That if I have triangles, right, two different sizes, as long as all the angles, the respective angles, are the same, then the two triangles relate to each other based on their proportional lengths, relative lengths. Okay? So if I define each side of the triangle, in this case by EF and D and small EF and D, then D by E will relate to D by E of the smaller triangle, and so on. Okay? So the relative lengths should remain the same. That's the law of similar triangles. And we can apply the same thing in order to understand our projection geometry. Right? So we'll simply break up our projection diagram into similar triangles. Right? In this case, I'll define triangles by the point in the 3D space at the distance c from the lens, right, in depth, and of course at height b in the xyz, and the projection of it a distance f from the lens and at a height small b. And similarly, you can define the other triangles. Okay? Now once I have the triangles, I can start relating their relative lengths. So A divided by small f is equal to capital A by C, and B divided by small f is equal to capital B by capital C. Right? So this tells me a very simple relationship that every point in the 3D world with coordinates A, B, and C will project onto my 2D plane, whose coordinates will be given by A divided by C and B divided by C, each one multiplied by a factor f, right, which is the focal length of my lens. Okay. Now f divided by c, you can think of it as a constant scale parameter that will scale every point in the 3D space to find its corresponding projection in the 2D plane. Okay. You can generalize this to f divided by z, z being the distance of an object in the 3D space from the lens. This f divided by z will be a constant scale factor. We typically refer to it as the magnification ratio. Okay. It's a magnification ratio that basically scales objects in the 3D world onto the 2D plane, imaging plane. Okay. It's a very simple relationship between 3D objects and their 2D projections. So, right, very simple examples, we can understand the relationships. If you have a man that's standing 10 meters out, okay, and is 2 meters tall, if I have a focal length, for my eye, generally it's about 17 millimeters. Question is, what will be the projection onto the retina? Right? And the answer is relatively simple. You essentially will have a projection which is 3.4 millimeters on the retina. Okay. So this simple geometry gives us a very simple relationship. Keep in mind that this is a simplified geometry based on the assumption of a pinhole projection system. Right? Think of it as a lensless projection system. The minute you have a lens, normally we do not have what we call a perspective projection system. We typically have what we call a weak perspective. Right? The assumption of perspective only holds true for perfect pinhole systems. You put a lens in, you are allowing a lot more bending of light. It's not only through the center that the light is going through, so we have a pinhole violation. A weak perspective comes into play. Okay? A weak perspective, we'll come back and look at it a little later. Okay? All right, any questions on any of this so far? Yes, I know. This time I'm looking at the time. We will stop here, but I just want to know if you have any questions on anything we talked about today. All right, very good. In that case, I'll see you on Thursday.